All right, so there are two major ideas here that we want to cover. The first one being that we want to be able to define surfaces parametrically. We want to be able to define our surfaces parametrically. And the second idea is that once we define the surface parametrically, we wanted to be able to define the surface area using the parametric definition from number 1. Using the parametric definition. So however we defined it in number 1, we're going to use that to be able to define the surface area. So back when we started doing this stuff in 2 dimensions, we have already done parameterization. And let's see a couple of the major types of parameterization. So we've used the trivial parameterization. And we've used polar. We've used cylindrical, spherical, so all those different things. Trivial and polar work better for 2 dimensions. Cylindrical and spherical were 3-dimensional parameterizations. So let's start off by talking about what we did in 2 dimensions. In 2D. So what we had was something like if we wanted to parameterize a circle, and we're going to carry this through to 3D. So, oops, there we go. We want to parameterize a circle. Maybe this circle has a radius of 3. The idea was if we wanted to parameterize a circle, obviously polar was the way to go for that. And what we would have done, we would have said, okay, x equals r cosine of t, y equals r sine of t, or theta, whatever we use. We're going to use r and t in this case. But what if we only wanted to do this for line integrals around the outside? We don't want to include everything on the inside, because if we do x and y equal r cosine and r sine, technically r could be any value. But specifically here, we are only interested in the outside ring. So I just want the outside circle, not the area. I don't want the entire thing filled in. So in this case, r is going to be a constant. R is fixed because in this case, r is always 3. So when I parameterize this, instead of it being x equals r cosine theta, now it's going to be x equals 3 cosine. I said theta, I meant t. And y is going to be 3 sine of t. So again, r is no longer a variable. R is now fixed. It's not a variable. Not variable. All right, and that's kind of how we would think about this if we did this in 2 dimensions. Now if we go to 3 dimensions, so now we'll talk about if we did this in 3D. So again, the idea is I've got some kind of a surface that I want to talk about. And again, I'm just going to go to a cylinder. We're going to just use a cylinder real easily here. So I'm talking about the surface area of the cylinder. So now the surface area, now this is going to be, I'll try and do my best to show this here, although it's not going to be the easiest thing. We are talking about the surface area of the cylinder. So when I parameterize this thing, I have to think about this in 3 different pieces. I have to think about the bottom of it, the top of it, and then the lateral face around the outside. And that's where it's going to get a little bit different. So we actually have to think about, okay, what does the bottom of the surface area of this look like? Well, now the bottom of this thing is a disc, so it does include everything. It includes the outside ring as well as the all of the inside. The top of it is going to be exactly the same thing. It's going to be a disc, so it's going to be the outside ring and exactly the inside stuff as well. When we get to the lateral face, it's not the inside. It's not what's inside of that cylinder. There's no volume to this, so it's just going to be the outside face, and that's where this is going to get a little bit different. So I'm going to do my best. I'm going to show you guys some stuff on CalcPlot 3D as well. Let's go ahead and define that we have these. I'm sorry, that should not be 4. I apologize. We're going to define the circles to have a radius, or this cylinder has a radius of 3, and the height is going to be a 4. That should make it a little bit easier. Okay, so let's parameterize the bottom of this thing. So again, we want the area of the whole disk. We want area of the disk. We want the whole thing. So in this case, R does have to vary. Okay, we need every single possible radius from 0 out to 3 for that bottom disk. And again, I can kind of shade this in. It's going to be the top, it's going to be the side part that I won't be able to do. We want that whole thing right there. So in this case, X is going to be R cosine of t. Y is going to be R sine of t, but we also have the z to talk about here, and well, this bottom disk is sitting flat on the xy plane, so z has to be 0. It's got no height to it whatsoever, so z is always 0 in that case. And what we've done is we've taken something which is in three-dimensional space, x, y, and z, and we have reduced it to 2 variables, r and t. And that's kind of what we're trying to do here, is we're trying to reduce the amount of variables from 3 down to 2. This will be something that's important when we start actually finding the volumes and the areas and the masses and all that kind of stuff. So what we have to do is we have to actually define our domain. That's a very important step. So we're going to define the domain. Well, t is the angle. And this is a circle, so t is going to go from 0 to 2 pi. It does go completely around the circle. So t, oops, let's try that again. There we go. So t is going to go from 0 to 2 pi. And then r, because r, we do want the entire disk, again, r has to vary from 0, which is right at the center, all the way out to 3, because I need every possible ring that can be made from 0 to 3 to create the entire disk. So r varies from 0 to 3. Okay, and hopefully I don't have to write out the next part for the full thing. For the top disk, this piece up here, everything's going to be identical except for the z value. The z value now is up at 4. So otherwise, this is going to be exactly the same. So this is the same as the that's just horrible. Same as the bottom, with z equaling 4. So it's going to be exactly the same thing. It's the lateral face now that we have to talk about. So the lateral surface area. All right, now in this case, the lateral surface area is going to be just the outside. And here's where I'm going to start to illustrate what I'm talking about. I'm going to show it to you on CalcPlot 3D, and then we'll come back and we'll actually write it in. All right, so let's look at this now on CalcPlot 3D. So the first one that we did when we parameterized the bottom, that's the one down here at the bottom, and they use U's and V's as opposed to R and T. It's the same thing though. The T and the V are the same thing. There's the angle, and then the R and the U are the same thing. But as you can see, the one down here at the bottom would be our R cosine T, R sine T, and then Z was 0, and that should give us the disk at the bottom here. Now I have put the parameters in there. There you go. From R would go from 0 to 3, and your T value would go from 0 to 2 pi. And, oh good, it still worked. I have this in airplane mode. I wasn't sure if this was going to work or not. There's our disk at the bottom, and you can clearly see that as a disk with the area of the entire thing, and it is from 0 to 3. And then we did the top, which is this one right here. Again, same exact thing, R cosine T, R sine T, but this time the Z value was 4. Again, goes from 0 to 2 pi and 0 to 3 for R. And then if we plot that, we can clearly see the top of the surface area of this thing. And then the last one is it's the lateral surface area. Again, we just want the outside. We do not want the inside of this. So this one is defined, as you can see now, there is no more U in the first two, in X and Y. It is constant. It is 3 because we are just talking about the outside. We are not talking about everything on the inside. So it's defined as what would be 3 cosine of T, 3 sine of T, because that'll give us just the outside. And then I define Z, well just technically Z can vary as Z, but in this case you can't actually input it as that. Z is going to vary as U, and we're going to let U go from 0 to 4 so that it's just the cylinder in between the two disks. And we'll take a look at that and see. And there you have it. There you have your outside of this thing. Now the hard part is here, no matter what I do, I'm going to try not to move this too much, but you can clearly see that this thing is a cylinder. The hard part is that how do I know that the inside isn't filled in? Well, that's a great question. I'm glad you asked. What we're going to do is we're actually going to change this so that it doesn't go from 0 to 2 pi. I'm going to do this from 0 to, let's do 3 pi over 2. So 3 pi halves. And what that should do, assuming that this works, is this should open up 1/4 of this thing so you can see the inside. Let's see if that works or not. And voila, there we go. Now you can see the inside is open. It is hollow on the inside. There's no guts on the inside of this thing. So anyway, there you go. There is your parameterized surface. But again, the major thing is that R has to be fixed in this case. The radius from the inside has to only be 3. That's the very outside ring. And then of course the height has to vary from 0 to 4. All right, so let's go ahead and finish writing our lateral surface area here, which again we said the outside has to be 3. So X in this case was 3 cosine of T. Y is going to be 3 sine of T. That'll take care of the outside part. And then we need it to vary Z-wise from 0 to 4. So again, we can let Z just simply equal Z in this case. Couldn't do that on the other one because it made me use U's and V's. But let's define our domain. T, once again, since it's a circle, has to go, that's our angle, has to go all the way from 0 to 2 pi. And then the Z value ranged from 0 to 4, including both of them. And that would create the rest of the cylinder.